Section 11.10, applications of Bernoulli's equation. To be fair, we already started the section in the last video. This is primarily the example known as Efflux speed. Efflux speed, by the way, is just a fancy way to say speed of liquid leaving a pipe. So it's an oddly specific term, but you can think of it as an exit speed, if you will. It says the tank is open to atmosphere at the top. Find an expression for the speed of the liquid leaving the pipe at the bottom. Right. So this problem, notice, doesn't give us a ton of information, at least not explicitly. There's a lot more that we could say implicitly. And so this example is perhaps best for highlighting that, right? Where it's information that you might not immediately notice. One is it mentions open to atmosphere at top. If it's open to the atmosphere, that tells you about the pressure, right? That the pressure at that point must be equal to 1 atmosphere, to just our standard atmospheric pressure. That's a key detail. Now that's at the top, which is labeled 0.2. What about at 0.1? Well, notice that's open to the atmosphere too. So the pressure there is also equal to 1 atmosphere. So as a result, we see that the pressure at 0.2 is equal to the pressure at 0.1, and they're both just equal to 1 atmosphere. That's a really key starting point, because once you recognize that, then you're able to subtract it from Bernoulli's equation. All right, some other observations. They just tell us it's liquid, which means it's incompressible, but they don't tell us what kind of liquid it is. So it's an unknown density. If in doubt, we could guess that it's water. That seems most likely, but they don't even tell us that for sure. So we'll just solve in terms of rho. Here I can write out symbol for rho. Cool. What else do we have here? The other thing that's pretty implicit is the size of the tank. And so something that, this is the one that I think is most uncomfortable. Like, I would prefer if they gave a little more explicit information here, but we're going to just note tank is large. Now, why is this notable that the tank is large? Well, if you have a really large tank, then it's going to take a long time for the water level to go down, right? Assuming this opening is not very big, which it doesn't look very big compared to that, that water level is going to take a long time to go. So the short and sweet part of what we're supposed to conclude from that is that v, the speed at 0.2, is approximately equal to 0 compared to the speed at 0.1, which is much higher. We could show that with the continuity equation. So if you're not comfortable with this, you could look at our A2 times V2, because this is what sets the speed of any fluid, is equal to A1 times V1. And so we get that the speed at 0.2 is going to be the ratio of the areas. Area 1 divided by area 2, and then times V1. If the tank is large, A2 is really big compared to A1. So this becomes a very small fraction, so that V2 does in fact come out to a tiny fraction of V1. So it is reasonable to say that it's approximately 0. You can fill in with your with radii that seem reasonable to you. Like you could say put a radius of 1 meter, and that becomes squared, versus a radius of maybe 10 centimeters. And when you square those radii and divide them by each other, you do find that it's a tiny amount of velocity. So because the tank is large, V2 we can say is equal to 0. Now with these ideas, along with Bernoulli's equation, we are armed to find the speed at the bottom. So let's take a look. So we're going to take Bernoulli's equation, the full detailed thing, but we note that pressure 1 is equal to pressure 2, which is just atmospheric pressure. That means we could call pressure 1, say pressure 2, right? Or we could call them both pressure atmosphere and subtract it from both sides, and it would just disappear. So this is actually a really rare case where the pressure is the same. Most of the time when we use Bernoulli's equation, we're going to have two different pressures. And so we're going to keep that term in there. But in this case, we were able to subtract it out. Because the pressures were the same, we have the unique situation where every other term does have the density rho. So because of that, we are able to divide by rho the density. But you want to be careful you're doing this to every term, right? This comes to 0, so that's why it's okay. And then these ones are just going to all cancel out. Wild. So there went those. Now, if we want to figure out our y1 and y2, y2 is going to be the elevation at the top of the tank versus y1 is the elevation to the spout. And we can notice that it gives us this height to work with. So if we want to work with that height or depth h, then we can relate that to y2 and y1, right? y2 is the full height minus y1 will give us h. And that's what this shows here. H is equal to y2 minus y1. So if we subtract y1 to the other side, we'd have gy2 minus gy1. So we can pull the g's out. We just have g times y2 minus y1. And we can call that then h, so gh. I guess here they waited to divide out the density, but what's left with v2 is equal to 0 is on the left we have 1/2 rho speed 1 squared. So with these dividing out, to show it once more since it didn't explicitly cancel, we can solve for v1 by multiplying by 2 and taking the square root. We get v1 is equal to the square root of 2gh. This is an equation we've seen before. Right? This popped up in, for instance, our conservation of mechanical energy. When all of our potential energy became all kinetic energy, we found that the speed at the bottom of the ramp was the square root of 2gh. What does this mean? Well, it means if we truly have an ideal non-viscous fluid, then the speed that it's going as it comes out the pipe at the bottom is exactly the same as if we had dropped the fluid from that same height. Even though it takes a different path, we'd have the exact same speed coming out. And that means if we turned our spout upward and it truly was non-viscous, the fluid would shoot up to exactly the height of the top of the water level. That the energy would be conserved, that if it started out with that potential energy at the top of the water tank, then it would have velocity at the bottom, and that kinetic energy would once again become potential energy. Now, in reality, it's not an ideal fluid, right? If it's water, say, it's going to stick a little bit to the sides. So it won't come all the way up to the same height, right? We're going to lose a little bit of energy in there. But this illustrates the idea that conservation of energy is still a concept that is undergirding a lot of what we're seeing. And this brings us to the end of chapter 11. So we've seen quite a bit here, introducing the ideas of pressure and density, and note they are different with different symbols. How pressure changes with depth as you go deeper. Also though, how pressure changes with velocity. If something is moving faster, it's a lower pressure. Velocity is set then by the cross-sectional area. So smaller area, like a narrower stream, stream starts moving faster. When the river gets wide, it slows down. This pulls all of the ideas of chapter 11 together. So I hope that it is flowing smoothly and steadily for you.